Hi everyone, thanks for joining the ARID seminar today. First, I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. I am Yovna Jangli, a PhD student in the Department of Statistical Sciences and part of the ARID organizing committee. ARIS is a partnership between the Department of Statistical Sciences at the University of Toronto and CanC, Ontario, and several other universities across Ontario. The goal is to increase discussion and collaboration between data science researchers across a variety of disciplines. Today, it's my pleasure to introduce today's speaker, Dr. Amy Braverman. Dr. Amy Braverman is a senior research scientist at the Jet Propulsion Lab. She holds a PhD in statistics from UCLA, after which she joined JPL as a postdoc. She worked on various NASA missions over her 23 years at the lab, first in designing data reduction methods for massive remote sensing datasets, and later expanding to address general statistical methods and application issues related to remote sensing. She recently began working intensely on uncertainty quantification at NASA and JPL. She is now serving as the chair of the SIAM activity group on uncertainty classification, aiming to bridge the gap between traditional math-based methods and statistics. Dr. Braverman is the recipient of the NASA Exceptional Public Service Medal for her efforts to bring rigorous uncertainty quantification to the NASA science enterprise. We'd like to thank Dr. Amy Braverman today for joining us to give us a talk on uncertainty quantification for remote sensing data. So if you have any clarification questions during the talk, please feel free to ask them. And if you have any substantive questions, please ask them at the end of the talk. Thanks. Thank you.
So thank you for the invitation to come and visit. I really enjoy coming to cold places in the middle of winter, as I can turn around and go home in a couple of days. I want to tell you that I am 3.5 weeks past a flu that I got on Christmas, and I am prone to hacking fits of coughing. And if that happens, I might have to stop and take these cough drops. And I think I have enough. It should work. It happened on the airplane on the way, and all the people around me were like, very, very frightened, but I'm quite sure there's no contagion. It's just a lot of hacking. So again, thanks for the invite. I always look forward to seeing old friends and make some new ones. I've known Meredith for quite some time. I've known BNA since at least last summer, where we met at JSM, and it's a pleasure to come and talk to you. And maybe some of this will lead to a future collaboration, who knows? And Deborah's an old friend as well. Okay, so I'm from JPL. Do I move this with the mouse here or with the arrows on the thing? Not with that. Okay. Anybody know how to advance the slides here? Maybe it's this way? No. No. Oh my God, it's froze. Anyway, I can tell you that many of you probably are familiar with the Jet Propulsion Laboratory. We are NASA's lead center for the robotic exploration of space. Every NASA center has a specialty. Although the lines are becoming somewhat blurred right now, the Goddard Space Flight Center is the lead for Earth science, and we are the lead for just that like that. Okay, thank you. We're the lead for everything not Earth that involves robots. JPL is also the first NASA center founded in the 1920s when a Caltech professor named Theodore von Karman was doing rocket experiments in his backyard in Pasadena, and the neighbors didn't like it. So they sent him out to what's called the Arroyo Seco, which was at that time uninhabited. It's not uninhabited anymore, but the dry river. And they did their experiments there. JPL became an Army research lab and then an Air Force research lab, and then became the first NASA center in 1958. And to this day, we're the only NASA center which are not civil service. So we're all Caltech employees. NASA pays for it. NASA owns the buildings and the equipment. but all of us have the luxury of being affiliated with Caltech. So today I'd like to talk to you a bit about one of the things we do. Obviously, we do a lot of things, but one of the things we do is Earth observation from space. And I want to tell you a little bit about how we collect data about the Earth system and what's involved in the processing, and in particular, how we might think about going about putting uncertainties on those data products that we produce. So you can see the outline here. This talk is mostly about the Orbiting Carbon Observatory 2 mission, which was launched in 2014, for which we were tasked with coming up with an uncertainty quantification strategy. But if there's time at the end, I'm going to talk about the Earth System Observatory, which is ESO. EOS is Earth Observing System, which was the first generation, the first big generation of NASA Earth observing satellites. The first of those was launched in '99, and they're still up there. They're still doing their job. But the next generation is called the Earth System Observatory. And the first of those missions is something called Surface Biology and Geology, SBG for short. But we'll see if there's time for that. Let's see. Okay. So remote sensing data are a very modern, comprehensive data source for studying the environment and the climate of Earth. Because we typically get global coverage, and we get it on a regular basis and over a relatively long period of time. These data can tell us things that no ground-based observations ever could. The issue is that no remote sensing satellite is everywhere all the time. They tend to be in an orbit that puts them in some places at some times. And all remote sensing satellites actually observe are spectra, right? So I think I have a slide on it later, but you fly along. Most the satellites that we work with are in what's called polar orbit, which means they're doing this. And underneath, the Earth is turning at the same time. So you're sweeping out these stripes. Think of putting Scotch tape on a basketball and spreading them out. And it can take, depending on how wide the strip is, it can take anywhere from, I would say, 3 to maybe 10 or 11 days to get global coverage of the Earth. The other thing is that, excuse me, all we see are these remote sensing spectra, electromagnetic spectra indexed by wavelength and the intensity or photon count in a discretized set of bins in wavelength space. And so anything else we're going to learn from this, we have to learn by doing inference, essentially. So, and therefore, I believe statisticians have an important role to play in lots of different aspects of this, in the design of the mission, design of the data collection, maybe the design of the validation procedures, because it would be nice to go out and collect some ground truth data to see how well we're doing. Here it comes. I apologize. We have not been as centrally involved as we'd like to be in the past, but I think the ESO offers a new opportunity to be involved. So uncertainty to statisticians kind of goes without saying. If you're going to put data through a processing pipeline, you're going to be injecting uncertainty along the way, and we should be quantifying that and keeping track of that so we can report it. Let's see. Okay, Earth observing system, circa 1999 to 2025. It's coming to an end. They're thinking about bringing those things down or letting them run out of fuel. The spatial scales of those instruments were on orders of kilometers. Even OCO2, which I'm going to talk about, has a footprint that's about one kilometer across and 2.5 kilometers along. A long track, where a long track is the direction the spacecraft flies, and a cross track is the opposite one. The new era of remote sensing is going to be the Earth System Observatory, which will have spatial scales on the tens of meters range. So the amount of data is about to explode. And anything that might seem mundane, any kind of processing step that might seem mundane when you're working with kilometer scale data suddenly isn't mundane and isn't easy or even necessarily possible when you're dealing with data that's that high. There are 4 new missions in the ESO, something called the Atmosphere Observing System, something called NISAR, which is a joint mission between NASA and the Indian Space Agency. It's a radar, surface biology and geology, which is the one I'm involved with at this time, and something called mass change, and has no better name than that yet. I did have I have a video here to play for you about the ESO, but I think I'm going to skip that in the interest of time. Okay, so at NASA and all the international space agencies, JAXA, ESA, the Canadian agency, the Indian Space Agency, everybody talks about remote sensing data as having undergone different levels of processing. So the data that are directly downlinked from the satellite are called level 0, that's raw data. There's a process called level 1 that involves georectifying, meaning every location on the ground associated with a spectrum is identified and tagged, also calibrated. Because we're looking at spectra, there can be different behaviors in different parts of the electromagnetic spectrum in terms of errors. And this all has to be kind of sorted out and made so that what's going on in one part of the spectrum is kind of comparable to what's going on in another part of the spectrum. And then this is where the magic happens, level 2, which are where you turn these calibrated and georectified spectra into estimates of real geophysical properties like temperature, or in the OCO2 case, carbon dioxide concentration in the atmosphere. There are a couple of further levels there. Level 3 is mandated for most missions, I think, although not OCO2, interestingly, that are so-called statistical summaries of the level 2 data on a uniform space-time grid. This is demanded because not every user in the world can handle the very large data volumes that are produced at level 2. And so typically what happens is you take your domain of interest, which might be the Earth, the whole Earth, and you chop it into, let's say, 1 degree latitude by 1 degree longitude boxes, and you pop the mean value of temperature in each box and maybe the standard deviation. In some cases, people start to look at covariances and things like that, but it's pretty rudimentary. Level 4 involves ingesting the data, either at level 3 or level 2, and doing data assimilation, right, which is an attempt to combine modeling framework with observations that supposedly drag the modeled values back towards what's actually seen. So the question is, how do we calculate uncertainties of the point estimates at level 2 provided by these remote sensing observing systems? And I'll go into a little bit of detail about how that's actually done. It's done, as you might think, with sounds pretty reasonable, Bayes' rule. Okay, so you've got an unknown, unobserved state vector, which we're going to call X, and you've got a corresponding noisy spectrum that we're going to call Y, and feels like what you want to do is get P of X given Y, right? Because that would tell you what the information is in your in the radiance that you have. But it's a very complicated thing to employ operationally. For one thing, you have to pick priors, to pick a prior distribution to do Bayes' rule. And there are lots of other computational issues involved in running that, which are not explicitly accounted for in the Bayes. If you just do it what I said, the only source of measurement error that is actually being accounted for in what I just said would be any measurement error on the Y. But there's lots of other things going on there. There are imperfect algorithms. There are computational shortcuts. There's failure to converge to the proper minimum. There's lots of other things that can impart uncertainty to the result of such a computation. So, let's go there. Okay, so here's my favorite cartoon. Many of you have probably seen this if I talk to you. This is a simple cartoon of what I would call a remote sensing observing system. The things in gray we don't actually get to see. It's the things in blue on the right that we actually get to see and have some control over. X is the true state variable, whatever that is. Maybe it's the vertical profile of CO2 concentration or water vapor, the brightness of the ground, the aerosol content of the atmosphere, typically a fairly large vector. Nature, I've called F0 there, as if nature actually had an algorithm that nature was going to employ, and there are some ancillary variables that I call B0 that actually, they're not part of the state vector, but they affect what F0 does. Notionally, nature produces a noise-free radiance, which is observed with some measurement error epsilon by our instrument to produce Y. Y is what gets sent to the ground. It goes through this multi-stage processing, and then it goes through what's called a retrieval algorithm, so named because you are going to retrieve from what you got to see the thing you wish you knew, right? And the retrieval algorithm itself typically works by starting with some initial guess for what the true state is, and then comparing what you would get if you put the true state into a forward model, which we wish was F0, but we don't know F0, so we have to use our own. It's called F1. And that really is an algorithm, and it really does have ancillary parameters that are called B1. And that's going to produce putting candidate X into F1 is going to produce, let's call it a Y hat, which is what you would get from a radiance in the way of a spectrum if X guess was the truth. Okay, and then you keep iterating on that until you can get as close as you can possibly get to the Y that you actually observed. So it's like least squares, right? But in this case, in the case of OCO2, it's Bayes. So you have among the B1s that are in there are the prior mean and prior covariance that you want to use in your process. So one way or another, what comes out of that is an X hat, an estimate of the true state. Now, in terms of the optimal estimation, there's something else that comes out, which is called S hat, which is X hat is the posterior mean of that distribution P X given Y, and S hat is the posterior covariance matrix. But it's actually calculated in a way that gives you pause. It's computed as a linear function of the X hat, which shouldn't be true. And in any case, I think it's fair to say it's widely accepted that what comes out of the algorithm operationally is too small. People don't believe it. So we were thinking about ways, excuse me, to do a better job at getting some notion of what the uncertainty is about X, given the X hat that we have. So uncertainty quantification as a discipline came out of mathematics and engineering as a formalism for putting uncertainties on the output of deterministic models. We statisticians, you talk to a statistician about uncertainty quantification, and I don't know about you, but I used to get in a big snit about it because we figure we do uncertainty quantification, right? We model things as random variables and we get uncertainties as well as estimates. But we don't do it for computational models. We do it by building statistical models. But there's an awful lot of people out in the world that build deterministic computational models to do stuff. And they wanted to be able to put uncertainties on their thing too. So that's what gave rise originally to the UQ community as a math thing. But statisticians like Bobby Gramercy, for example, or Dave Higdon, a bunch of people have worked really hard. And these things are starting to merge a little bit. And so I think the rule of thumb is, depending on how much you know, you would choose either a statistical model or a deterministic model. If you thought you knew a lot about the system you were modeling, you would use a deterministic model. If you thought you didn't know much at all about the system you're modeling, then you might use a statistical model. And I think there are places in between that one could be that have not really been explored. In terms of our problem, we have a number of sources of uncertainties. I think I already said what these are. The only thing I didn't already say is that we also have to cut some corners because this retrieval has to be fast. It has to keep up with the downflow of data from space. So here's a little bit about the orbiting carbon observatory. You can see on the left there's a bunch of ground tracks for OCO2. It takes 16 days to repeat the exact same set of strips that you see there. The measurement principle, I don't want to say it's simple because Deborah's in the audience. It's not simple, but photons come from the sun. They pass through the atmosphere on the way in. They are affected by what they encounter in the atmosphere. They hit the ground. They are affected by what happens to them when they hit the ground, what they encounter, and then they go back out and they are affected again. And the measurement principle is that we can actually figure out from these spectra, you might say what the influence of a certain amount of carbon dioxide at a different altitudes are, how that affects the spectrum. And the idea is to use that fact to try to infer the amount of carbon dioxide in the atmospheric column based on the spectrum that you see. There's a little cartoon of the instrument there. I guess it's a big camera, right? And it's doing this discretization. And what it also does is, so it discretizes the spatial field as you see over there on the right in ground footprints. And the reason they're parallelograms is because of things moving, I think. So every one of those little parallelograms, there are 8 across, that's superimposed on Washington, DC, so you can get an idea of what the scale is, contains a 3048 length vector of radiances. And these, we talk about 3 different sections of that, each of them 1016, I guess. The O2A band, the weak CO2 band, and the strong CO2 band. So they're contiguous within, but I think there's a displacement between them in spectral space. So here's our problem. Our retrieval uses that 3048 dimensional radiance vector to try to make an inference about a 45 dimensional atmospheric state vector. 20 elements of that atmospheric state vector correspond to CO2 concentration at different altitudes. The rest of it is this stuff like aerosols and ground brightness and all that. Let's see. Okay. That process, that retrieval process is fragile. And the mission made the decision that in order to deal with that fragility, what they were going to do was not report the individual CO2 concentrations going up the column. They were going to average that. They were going to do what's called a column average, which is just a linear combination of those 20 elements that give me the CO2 profile. And that's what I'm going to report. So if I can get the posterior distribution of X given Y, and I take the expected value of that, let's call that bold X hat. That would be a vector. And if I then throw away everything that's not CO2 and average what's left using a pressure weighted average that assigns a different weight to different altitudes, I get this thing called X hat, which is known in the community as X CO2. I think X is traditionally the column total notation. Like I said before, we also get this thing called S hat, which is the posterior variance of that average, but there are issues with that. So let's see. OCO2 uses this optimal estimation, that's the computational implementation of Bayes, to retrieve the maximum a posteriori estimate X hat, which is it's actually the mode of the posterior. But under Gaussian assumptions, which is all over the place here, a linear combination of Gaussian random variables is also Gaussian, and so we are asserting that there's a normal distribution out there for each footprint that has a mean of X hat, meaning a mean X CO2 value, and it has a posterior variance of this S hat number. So X hat is treated as the posterior mean, S hat is treated as the posterior variance. Okay, so let's look at this a little more. I think I said a little bit of this earlier. There's the cartoon again. Under optimal estimation and under the operational view, the retrieval itself is trying to find this posterior distribution of state-given spectrum. Our view, my view, is that's not actually what we want here, because, as I said earlier, the only thing considered uncertain about that is Y. And there's all these other things. There's wrong choices of B's, there's convergence problems, there's all kinds of things. So I would assert that we should be interested in the posterior distribution of X given X hat. So I've got this black box algorithm that pops out a point estimate of what I think X is. And if I could get a grip on what that conditional distribution is somehow, then when you bring me a real X hat that was produced by my data processing system, I could plug it in there and I could produce for you a posterior distribution of X for that X hat. So that's what we're going to do. And we went that way because a lot of people would take the view that we want to sort of try to write down all the possible sources of uncertainty that are created by this system and try to forward model them through, just propagate them through. And I said, oh God, that's never going to work because we don't know what they are. We know some of them, but we will never be able to write down all of them. Not to mention the fact that there are second, third, fourth, high order interactions of all these things that we can't even hope to think about. So we said, what can we do that is more top down rather than bottom up, if you know what I mean? I gave it away already. The essential idea is to use a simulation experiment to estimate the joint distribution of X and X hat in a simulated environment. We're gonna estimate that joint distribution as a Gaussian mixture because we don't want to constrain ourselves just to linearity and Gaussian. Once we have the joint distribution, it's easy to condition a Gaussian mixture and get a conditional Px given X hat from that conditional. We estimate the parameters of that from this simulated system. The estimated Gaussian mixture model for a new X hat is just found by plugging in our new X hat into the formulas for the regression means and variances for each component of the Gaussian mixture separately, and then simulating from that distribution. We have a name for that now. We call it a Gaussian mixture inversion, which somebody else has taken, somebody else at JPL, one of my young colleagues, and is trying to turn into a thing, bigger thing, like something that could do a retrieval, for example. So here's again, a cartoon of what I'm talking about. So the idea is to learn a relationship from the simulation experiment. Everything with the sim is simulated. So we have to collect up a set of an ensemble, I'm going to call it X sim with the curly brackets, an ensemble of representative values that we think are, that ensemble is representative of what our satellite is likely to see. And of course, we can't ever know for sure that we've got that right, but we're going to do the best we can. Just like when you're doing Bayesian modeling, you do the best you can with the prior. If you're going to put a prior, you got to get one from somewhere. So I'm not quite sure how. I know how we did it here, and I'll tell you how we did that in a minute. We have our forward function that we're going to apply to every member of that ensemble. We're going to get some noiseless spectra from our forward model. The forward model takes us from a state to a spectrum. And then we're going to do two things. We're going to add the measurement error, and we know the statistics of the measurement error from lab studies. And we're also going to do something to penalize ourselves for what will turn out to be an inverse crime. Excuse me. The observation ensemble that comes out of that forward modeling step, I'm going to put that into the retrieval, but notice that in orange there, what I've done there is I've used the same model F1 here, which is the best model I have. Remember, I don't know what F0 is. And I'm going to use the same model here as I used in the forward function there. And that's not fair, right? That presumes that the forward model used in the retrieval is exactly knows what nature has done, and that's not true. So what we're going to do is we are going to corrupt this ensemble of synthetic spectra by taking an independent random draw from what we call the model discrepancy distribution, which for our purposes here was a multivariate Gaussian with a certain mean and a certain covariance matrix. And I have 3 whole slides on how we estimated the mu and the sigma there, but I'm going to wait till the end to get to that, see if we have time and if anybody's interested. But what we did was we were able to do that with a combination of simulation and real data. So I'm just going to leave it there for now. Let's assume that YSIM has been suitably fuzzed up. Our retrieval pops out an X hat sim, and now I have this joint ensemble X sim, X hat sim. And now I can try to understand the relationship between the truth that went in and the estimate that came out. So what I'm trying to interrogate here are, you might say, the statistical properties of this pipeline. So I have that. I'll fit my Gaussian mixture model. I'll get my P tilde, which is the Gaussian mixture fit to that ensemble. And then I can condition, and let's say I have capital K modes or capital K members of my Gaussian mixture components. For each one of them, I have a mean function, I have a covariance function, and I have a weight. And in order to simulate here, all I have to do is you give me a new actual retrieval, X hat. I simulate with the proper weights from that distribution. And then I can look at what the thing looks like. I have it. What did I do about the model discrepancy? I think I said that. Oh, what did we do? The synthetic ensemble to start with, and this is going to sound really strange. We used actual OCO2 retrievals there. because it doesn't matter what it is. It just has to be representative. It's not going to be perfect. But what I'm aiming to understand is the relationship between X hat and X, and I can use any known truth that I believe realistically represents the way nature works to do that. Okay, so here we are. This is Gaussian mixture modeling stuff. I don't think I'm going to go through this. A Gaussian mixture model is a set of Gaussian bumps. Each bump gets a weight. Each bump has a mean and a covariance matrix. And really what you're doing when you draw from a Gaussian mixture is you're picking a bump at random according to these weights, these pies. And then once you have identified the bump you're going to use, then you draw a Gaussian from that and you write it down, and you do that about 10,000 times. And now you have a pretty flexible distribution that can be nonlinear and non-Gaussian. Okay. So we did this with R. I'm not gonna dwell on this. That's the standard function for the kth component, the standard prediction equation for the mean, given some new value U. Okay, now I've gone and I think I'm gonna show you something in a minute that will help clarify this. But I think we're just gonna go ahead and assume everybody is okay with this. We have a way from the data to estimate the means and the covariance matrices and the mixing weights, and that R package mclust will do that for you. Okay, so the conditional distribution of W here, I've changed the notation a little bit. W is the variable I want to predict. U is the variable whose observation I have seen. That would be like Y. X would be like W. And I can sample from this distribution in the following way. It's what I just said. Pick a bump at random, then sample from that bump. Pick a bump at random, sample from that bump, and so forth. Okay, so here's the cartoon one-dimensional example. Here's our forward model over here. And the forward model is nonlinear and is differently variable in different places. W is like our true state X, and U is like our X hat. If I flip it around, then I've got U on this axis and W on that axis, and I just change the scale by standardizing. Now, if I were to try to fit a single Gaussian to that thing, it wouldn't fit very well. Single Gaussian plopped on top of that gray set wouldn't fit very well, but if I fit 6 Gaussians to that, looks like it fits a lot better. So that's all I'm doing, is I'm going to use this software to sort of fit those 6 Gaussian bumps there. And then for any position along this axis, if you want to know what the distribution is, let's say I pick one value down in this area and one value up at that area. Down here, I would just be doing a vertical slice through all of those ellipses. And the way I've drawn this, you can't really see that the blue ellipse really does extend all the way down there. So what I think I should see is, I think if I condition down here, I think I should see a slice through here that gives me a posterior distribution of W that is wider here than it is here, and has a lower mean here than it does here. And in fact, that is what we get when you do that. So here I picked something that had a U value that was down at the low end, and on the right, I did it up at the high end. So that seems rather pleasing. They look relatively symmetric, but of course that doesn't mean they're Gaussian, right? In fact, they're not Gaussian by construction. So when we applied this for OCO2, the devil's in the details. Now we have to make a whole lot of hard decisions. The synthetic true state ensemble, I told you already that we actually got a big collection of OCO2 data together and said, that's going to be, we're gonna take, in fact, they do retrieve the 20-dimensional column. They just don't like to report it. We're going to take that 20-dimensional column. We're going to take all the other retrieved quantities that they got for that state vector X. We're going to say that's our X set. We did land and ocean separately. We partitioned the land regions into 11 partitioned land into 11 subregions. I think we did 13 ocean regions, but I think I'm only going to talk about land here. And I'll show them to you. I'll put in a plug for I was going to say for Deborah, but this isn't TCON. This is not TCON. This is something else, right? So here are all our land and ocean regions, and we just went to the scientists and said, cut up this map in a way that you would feel comfortable treating information from within any one of these areas as, I don't know, what would maybe I'd call it, I might say ergodic, but I'm not really sure exactly what that means in this context, so I probably won't. But I just wanted to see, where do you expect this process, this CO2 process, to be moderately homogeneous? As if, what's going on in S12 over there on the left side of S12 is kind of equally informative about the underlying true process in that area as would be a draw from the right side of that area. And this is what they gave us. I'm trying to think what this is called. It came from Andy Jacobson and his flux inversion friends. And it has a name that I can't remember right now. There was some big experiment that they did where they tried to get fluxes for all these different regions, and now I can't think of it. I'll think of it later. What's that? Yes, that's it. The Transcon regions, these are called. Okay. So what we did was, now I get to put a plug in for Deborah, right? We took, I think we did only the land regions here. And for each one of those regions, we built one of these mixture models. And we did it, I think we did it by month. No, we did it by week in this case, over 4 different months. That's what we did. We did 4 weeks per month in each of these 4 months, in August 15, November 15, February 16, and May 2016. And the only source of ground information that we have to evaluate how well we did is the TCON network, which is total carbon column observing network, which Deborah here, your colleague, runs. So if you have more questions about that, we can refer to Deborah here. But these are places where instruments have been set up to actually measure CO2 on the ground. And when I say actually measure, you got to take that with a grain of salt, because those sensors also have to do a retrieval to get to their estimate of what CO2 is on the ground. So it's not exactly ground truth, but it is generally treated as such in the remote sensing community because it's much closer to whatever ground truth is than what we're getting from the satellite. So there are a number of different TCON sites. I think I have a slide about where they are. And what we wanted to do is we wanted to evaluate how well these Gaussian mixture distributions on a pixel by pixel basis, right? We built a model from a collection of data for each of those land regions. And then I'm sorry, I misspoke. We did not. I believe we put them all together and we built one model per week for these guys. Maybe it's just better for me to go ahead here. What we wanted to do was evaluate how close our distributions were to what TCON was telling us. And I'll show you how we do that, because TCON is just a point value, right? So we're basically going to use something like a PIT score or a CRPS, one of those, to try to evaluate how consistent the TCON measurement was with the distribution that we came up with and the operational distribution, which is essentially a normal distribution with mean X hat and variance S hat. And we were going to look at 2 different metrics of fitness here. Where in the distribution, this is the PIT thing, right? Where in the distribution did that true TCON value fall? Should be near the middle, I hope. And what the bias of the distribution in question is relative to that TCON value, because you would hope that the center of those distributions would align with the TCON value. So those are the total carbon column observing network, right? That's the right order. Okay, so this is where they are. This is really good for remote sensing validation data. This is a lot of places, but it's not everywhere. And it's not necessarily in the places. It's not equally representative of all the places that we might care about, right? There's not very much out in the ocean. Most of it's in the Northern Hemisphere. So we're going to see what happened. Okay, so here now, what I should say is, okay, so there's a TCON station in a place called Lamont in Oklahoma, Southern Great Plains. There's a TCON station in a place called Scuba, Japan. And what we did here was we found the OCO2 pixel, very tiny, that actually overlapped those locations on the day that OCO2 flew by. Okay, so we went to date, we looked at only the orbits that actually overpassed these stations. When we got an overpass, we looked for, so TCON is taking data quite often, but not necessarily at exactly the moment OCO2 passes over. But we were always able to find one that was very, very close. I can't remember quite what the time lag was, but we literally went to the pixel that contained the TCON site. We didn't do, it's customary in these kinds of problems to maybe draw a box around the TCON site and say, well, you're gonna go 30 kilometers this way, 30 kilometers that way, 30 kilometers that way, 30 kilometers. That's a coincidence region. We didn't do that. We went to the pixel that had the thing in it, and we were within milliseconds, I believe, of the overpass in the temporal dimension, because we really wanted to see what we're going to get. And so the green bar is the actual TCON value that we declared to be coincidence. The blue distribution is that operational Gaussian distribution, which you can see is quite narrow in most cases. And our distribution, the one we got, is in red. And this is just a sampling of the kinds of things that can happen. There are cases over there on the left. The red distribution looks pretty good, the blue one not so much. On the right, up at the top, they both look pretty good. Down there at the bottom on the left, neither of them looks very good. And this one on the right, the red distribution looks better, but the blue distribution isn't awful. It's within the realm of possibility. But this here shows you that you can get multimodal things out of this. So instead of showing you a bazillion of those pictures, I'm going to show you a plot in a second that has two axes. One axis is metric 1, the other axis is metric 2. XT is the TCON value. The OP is for the operational. The S is for the simulated. And the G is that essentially that pit score, right? Where in the distribution do you fall? A good score would be a half in that respect. Metric 2 is simply the bias between the operationally retrieved estimate X hat or the simulated estimate of what the mean would be, which is just the average, the empirical average. Okay. All right, so there's the summary plot over a total of 944 different coincidences with TCON stations around the world in those 4 months. And where you want to be is in the lower left. You want low bias, and you want to be near 0.5 here, right? And 63% of the time, at least in the, I'll show you a table with the actual numbers in them. We were in that area where the simulated distribution was superior on both of those metrics. 25% of the time, interestingly, the operational retrieval gave us a better bias behavior than ours did. 11% of the time, I think the operational retrieval is better on both metrics than us, and we didn't have any cases down here in the lower right. So let me show you some numbers. Oh, I guess I'm not ready to show you numbers yet. What I really want to know now is about interval coverage, that if I made intervals from those different distributions, how often would they contain that true TCON value, right? I want to know whether my coverage is good. So again, I have the lower and upper 95% quantiles, or the 0.5 and what is it, the 0.25 and the 0.975 quantiles of the simulated distribution. I have the same thing for the operational Gaussian distribution. And I have these two intervals that I want to compare, and I want to look at the number of times the TCON value was actually in those intervals. For, I think we did alpha at both 50% and 95%. And here's our result. You might figure it out. Green is good, red is bad. These are the different TCON locations. The operational retrieval found the TCON value in the implied operational 95% interval only 1.3% of the time. The 50%, it didn't even make here. Whereas we have overcoverage, you might say, for the 95 and 50% intervals for the simulated distribution. We did have a few places, in particular, let's see, Lauder, New Zealand. We didn't quite get where we wanted to go there. These numbers, this should be 95 and 0.5, where I have the 0.932 and 0.441, but it's not terrible. It's not awful. Let's see, this is overcovers here, undercovers there for Orleans. And then there's everybody's favorite Sodankula, Finland, which is at a very high latitude. There were only 15 cases there. And we didn't do particularly well there, but that's a notoriously hard place to get good retrievals, actually. So it doesn't surprise me. So this is kind of the story. If I had to point to one slide, this was our validation study of the uncertainties, and we were moderately happy with it, happy enough to put it in a journal paper. So let me see, what time is it? It's 4:16. Let me just tell you a little bit about what's coming up. As we move from the Earth observing system to the Earth System Observatory, I already mentioned that we're going to have this explosion in data volume. We're also going to have an explosion in complexity of the UQ problem. The new mission is surface biology and geology. It is going to be, it's actually two separate spacecraft, one of which observes in what's called the visible shortwave infrared, and the other of which observes in the thermal. And the visible shortwave will, actually the dimensionality here will be lower than it was for OCO2. The OCO2 dimensionality was very high, and I think I forgot to say that in fitting those Gaussian mixtures, we did a principal component dimension reduction of both the spectra and state vector, and then unwound that at the end. I should have mentioned that, sorry. So what's going to happen here? Two platforms, mostly separate processing streams, 30 meter on the ground for the V square, 60 meter on the ground for the thermal. And what's different about this than OCO2, but it turns out it's not actually different, but I'll clarify that in a minute, is that there are two separate streams here. This is, remember my earlier picture, my little cartoon that had X over there, and then you went through the forward model, and then you got to your spectrum, and then you got your measurement error, and then you went through a retrieval, and then out came an X hat. That's analogous to what was in the previous picture. But now we have two separate pieces that come out here. And I've added another thing here, which is this part here, which suggests that, let's say there's a number of geophysical quantities that you're interested in here. Maybe it's mineral content, vegetative properties, amount of snow in a pixel, any of these things. Those are the things you really care about. I chose to call those theta, and I chose to say, for purposes of the cartoon, there's capital K of them. There's some latent function, f-1, that converts theta into what we call an intermediate state vector. When I said that xTIR and xv were the analog of x in the earlier cartoon, I kind of misspoke there. I kind of didn't say that right, because in the OCO2 case, it was as if we went straight from theta, which are these true atmospheric characteristics, straight into there. Here we have straight over to here, actually, straight over to these things. Here we have what are called surface reflectances. And all these are the original spectrum generated by nature for a given set of physical states, as they would be seen if you measured them on the ground rather than top of the atmosphere. So a key part of retrieving surface information is removing the impact of the atmosphere, because you want to know what the spectral characteristics of the ground are. You don't want that pesky atmosphere in the way. So there's a big literature in the remote sensing community on something called atmospheric correction. But in fact, all it is trying to infer what you would see on the ground from the radiance that you actually observed, right? And so here what we've done is we've said, here's the true physical state. These are these notional true surface characteristics, these, surface reflectances, which are the spectra on the ground. Those then go, each of those, one for thermal, one for visible, goes into a forward model that yields a radiance. And in fact, this is a surface-only radiance, basically, right? There's measurement error, and then you go into that retrieval, which is analogous to the retrieval we had on the earlier page, and it produces estimates of these intermediate states, which are the surface spectral properties of the scene. And then those become the inputs to geophysical algorithms that are designed to recover the states themselves that led to it. So what I've done is I've clamped an extra step around this, right? I've said, gee, if I was gonna do the simulation experiment the same way I did it before, I'd have to start with some notional ensemble of true states here. I'd have to know what that function is to know how those true states translate into surface spectral properties. And then I'd have to run the whole thing forward again, and I'd have to go through 2 steps. I'd have to go through 1 step to try to recover these guys, and then another step to try to recover these guys. So that's quite a bit more complicated than what we just did. Only it turns out it's not, because in OCO2, it turns out people don't actually care all that much about XCO2. I mean, I think there's a lot of scientific reasons why they could and why they should, but the primary use of those total column carbon dioxide estimates is to put them into data assimilation models designed to recover the flux of carbon from the surface to the atmosphere and vice versa. So there is that second step at OCO2. We just didn't know about it at the time we invented our methodology. So I only put this up. I didn't mean to confuse or muddy anything. I only put it up because I wanted to emphasize that the problem's not going away. In fact, it's getting worse, right? It's getting more complicated. There's more stuff to do here. And it's a good thing we have till the end of the decade to figure it out. Okay. All right. So some discussion points. What time is it? Close. Okay. All right. Our challenge was to develop a practical method to assign uncertainties to every estimate produced by a remote sensing observing system. And the word practical looms very large. We were told when we started, the retrieval algorithm, the operational processing pipeline, that's all already built. It's there. It's doing its thing. You may not interfere with that in any way. You can't add anything to it. You can't ask us to do anything else. You have to just work with what comes out of it, what goes in and what comes out. Uncertainty here, I have defined as the conditional distribution of the true state, given the estimate that my processing pipeline produces. I'm just going to treat that like a black box. A friend observed to me that the method here is a little bit like the bootstrap bias correction, but applied to the entire distribution, not just to the mean of the distribution. So in the bootstrap bias correction, you resample the data that you have, and you pretend in your mind, so you start with a sample. Your sample came from a population. You take subsamples from the sample, and then you pretend that the sample is the true population and the subsamples are your sample. And you look at the estimates that you compute, let's say for bias, you look at how they compare your estimates from the subsamples to the synthetic truth in the true sample. And you assume that that same relationship holds between the one sample you have and the population. That's kind of the idea. And here it's the same kind of an idea. It's just that we're doing it as a whole distribution, not just to a parameter of the distribution. The simulation-based confidence intervals are usually valid in the sense that they usually, I say with a grain of salt, valid in the sense that they achieve at least as much coverage as the advertised, not in every case, but in some of those cases. But they're not always efficient in the sense that they're not always the smallest that they could be. And you do want that. You want your intervals to be small. The additional challenge for SBG includes the massive data volumes, the high dimensional quantities of interest, the 2-stage processing, constructing ensembles of quote unquote true synthetic geophysical states, those thetas, right? The Gaussian mixture model thing was pretty good. It allows us to to not restrict ourselves only to Gaussian behavior. But remember, we're doing this pixel by pixel. So we have not been able here to retain any of what you might call cross UQ or the cross uncertainties between pixels, right? Which are kind of analogous to covariance. And been working on a different idea for that involves simulation of spatial fields, but that's not ready for prime time yet. And I guess that's what's at the bottom there, which is, okay, you give me a spatial field, I'll fit a spatial model to it and I'll simulate from the model. Now I have an ensemble. And I have an ensemble of individual realizations of that spatial field that preserves the spatial structure. And so I can interrogate, let's say, how often a value is likely to be high in pixel A and also high in pixel B. Turns out modeling these spatial fields is really hard. I've been whacking away at that for about a year, and it's really, really hard. And maybe because I never had the spatial statistics class, I suggest everybody take a spatial statistics class. I'm having to learn it on the job here the hard way, right? They say an expert is somebody who's made every possible mistake. And that's me. So yeah, take spatial statistics. All right, here I have some references here for some of the things we talked about. There's Deborah Wunsch's paper down there on the TCON sites, which might be of interest to anybody who's kind of interested in how we do this kind of validation. And I'll put this one up here. This is a paper we wrote that basically describes the methodology the method that I talked about. And then I think we have to do the legal here. There's the legal part right there. And I'm anxious to hear your thoughts and talk to anybody who might want to collaborate on some of this further. Meredith knows where to find me and VNA. Okay, that's it. That's ran a little long, sorry about that.
Thank you, Amy, for a great talk.
Okay.
So we have around 5 minutes left on questions.
Oh, boy.
Just curious for the Gaussian mixture model, I looked it up and I saw that it's finite Gaussian mixtures.
Right.
Do you care about like assigning an observation to a component, or is it just the flexibility?
No, it's just the flexibility. There is no hard classification involved here. It's just, you've got this much probability belonging to that one and that much probability belonging to that one. Is that what you mean?
Yeah.
I should probably read your paper, but I'm gonna ask this anyway. So you came up with a method of assessing the uncertainty.
Mhm.
But of course, does this go into the operational data flow? Like, do we get access to those uncertainties? How do we use what you've done to assess the uncertainties that come out of those to retrieval and then replace them?
Right. John Hobbs and Joachim are running that right now.
Okay.
It's done afterwards, hence the name post hoc. But the plan is, we could, the plan is to get something into the light files. The light files are a trimmed down version of the full data product that OCO2 produces because the full data product is really, really big. So probably some measures, you'd get the median and the mean, that'll give you an idea of skewness. And some other quantiles, most likely, and maybe a determination of whether the distribution is Gaussian or not.
So there's like an XCO2 uncertainty in the light files. And I was wondering if you knew like how that was calculated or if it's related at all to.
That's the S hat. That's what the optimal estimation algorithm produces as the posterior variance. That's the thing that was too skinny all the time. In the blue ones. Yeah. Yes.
It's probably too long of a question for, but I was hoping you would say a few words. The delta term that you have, I would imagine that actually has quite a big impact on the.
Yeah. Yes.
So how do you choose?
Okay, yeah, I'll just throw this up. Okay, so there's a 3-slide argument here. It said we want to approximate delta sim is the difference between what the true forward model nature produces at the true state, minus what our forward model would produce at the true state, right? We have the first thing, that's what we observed from the spacecraft with error, mind you. We don't have the second thing. What we have for the second thing is this, our model evaluated at the estimated state. So here's a little clever add and subtract thing where we essentially are trying to capture the difference between this, which is what we've got, and this, which is what we wish we had. And we're learning the difference between those two things from the simulation. So then you can do a bunch of algebra. And if we're just going to say for convenience, and I bash other people for this all the time, but let's just say it's all Gaussian. Then I need the expected value and the covariance matrix of that Gaussian. And I can do this bit of jiggery pokery here where I'm kind of swapping in and swapping out the simulated versions of things and the actual observed versions of things. And I can get it down to this, which is that the mean of that distribution, because the mean of the measurement error is 0, the mean of the distribution is just the mean of the observed radiance minus what the model predicts. That's the F1 evaluated at X hat minus the same quantity produced in a simulation experiment. And then to get the, I realize that may not be entirely clear, that's in the paper if you want to go read that paper. Covariance matrix argument is a little bit different. It's an upper bound here. Here's the usual thing. Here's the covariance of something. It's the covariance of the first thing. That's, this is the difference in the real data. This is the difference in the simulated data. And here's the covariance of those differences. And I assert that if the covariance of those differences isn't positive, then we're in real trouble. I mean, we think it's good enough to assume that the simulation experiment will lead to a result in which this covariance term is positive. And then I can just use the usual thing. I just whack it off the back end, move the covariance of epsilon over to the other side, and I end up with something that looks about like that. So that was the sort of the shell game of trying to figure out what we could do about that. It turned out it didn't work very well at first. We had to use bias corrected data in order for that to work effectively. And we discovered, we knew we had a problem when the simulated ensembles, the synthetic X hat distributions didn't look like the distributions of X hat that we used as our synthetic ensemble. They had sort of different properties, but once we moved over to the bias corrected X hats, that took care of it. Yes.
You showed earlier there is like a map of stations where you get the ground truth of the measurements on the ground.
Yep.
How, I guess, limiting is it in terms of you want to measure uncertainty, but you only have that finite number of stations. Like in an ideal world that you have an infinite amount. I'm just wondering, like, do you think you'll ever be able to get somewhat close to like good uncertainty estimates given all we have is that?
Well, that was the point of doing what we're doing, right? Which is to say we need a way to do it that doesn't rely on having ground data because we're never going to have enough ground data. We need some kind of scheme. So what we really do is we keep the ground data to validate the method, and we can apply the method anywhere.
I guess my question was like, you mentioned the one that was like far north.
Yeah,
was in Finland.
yeah.
You got to think there's probably other areas of the earth that are sort of similar to that. So like, is that like a really big problem in your eyes, or do you think like this method will,
Excuse me. We're not there yet. I think what we've shown in that paper is that there's a path forward and that it could be, I think what we're going to have to do, we are probably not going to ever have more than this for this. Is that fair? But you have your EM27s, right?
I mean, there are more T-cone stations, but not substantially more than.
Yeah, I mean, we're never going to have some kind of uniform coverage where we can say that, Now, people do make the kinds of approximations, when they do this, they do a bias correction to the reported XCO2, this total column carbon number. That, because if you didn't do that correction, the numbers were too far off. I think it would be fair to say they were unrealistic. And so they decided that there had to be this post hoc correction procedure. And they did that by making a number of approximations. Effectively, there was some regression analysis on the data from these decon stations. But there was also, correct me if I get this wrong, there was also something called a small area approximation, where they said that we know as scientists that CO2 does not change over regions of size, what was it, 100 kilometers? Was it that big?
I don't remember, but it was just the right idea.
Some thing. And so we're gonna sort of make that assumption that, you know, what you're seeing there is the average of a bunch of things within that, and that it's the true mean, the true value for that entire little plot is whatever the mean is. So there's a lot of really clever things that are done that can only be done with domain knowledge to validate the instrument. And I think that, like I said, I think we've got a ways to go before people are going to accept this idea. And we'd want to, again, check it more carefully. We've rerun it now with the latest version of the OCO2 data, which is more realistic than the version that was used on this. And I think, you know, depending on how many times we have the luxury of being able to refine the method and redo it, and how many times we have the luxury of their reprocessing to fix things, we might get reasonably close. You know, there's no ironclad guarantee, right?
So we have two more questions.
Okay.
So the first question is, so the new sensors are going to provide very different data compared to the current sensors. Are there techniques to ensure that the values estimated from both sensors will be compatible for long term?
That's a really good question. In fact, that's the same question that the review board, who just hammered the SBG mission team, asked. And it's funny because there doesn't seem, they're right now they're treating these two parts of the mission as independent of each other. Makes you wonder why it's one mission, but there they are. And there was no formal requirement for that. It's only been, people are only beginning to start to think about that now when we raise the UQ issue. Because if you ever want to use data from the visible sensor to the data derived from the other sensor, you're going to need to know that that their uncertainties are meaningful. And when we start asking ourselves about what people are going to do with these things, they're going to be using the two things together. And so I personally will take credit for having raised that issue. So thank you for your question. We're a little bit too much at the beginning of this for people to do more than drink beer and talk about it, but eventually it's going to come up to the top. And the other question.
And then one last question. So question on slide 12. What is the sensitivity of this method to F1?
Good question. So we managed to dodge that question. It would be certainly possible to answer it by changing F1 and putting it in there. The F1 we're using is the same F1 that they're using in the operational retrieval. So we said that's not really up for debate at this stage. That's one of these things we are conditioning on. We're conditioning on doing whatever the mission is doing because we're trying to reproduce their process. The sensitivity of F1, excuse me, I think people think they understand radiative transfer pretty well. Radiative transfer is the science of how photons are scattered and absorbed and otherwise changed by encountering, going through different media or bouncing off different surfaces, that kind of thing. And most of the F1s that we have here are pretty good. Let's make a joke, good enough for government work, right? There are shortcomings. I believe these are all what are called 1D radiative transfer models, which means that I think what's tracked is just when a photon encounters something, it bounces off in another direction, and that's the end of the story. If the photon bounces off and bounces in a different direction, do I have this right? I probably don't. 1D, what's the difference between 1D and 3D?
Multiple scattering is taken into account.
Okay, so I am right, right.
Algorithm.
I got you, right. So photon comes in, it bounces out. In 1D radiative transfer, that's the end of it. In 3D radiative transfer, it comes in, it bounces, it bounces, it bounces. It keeps bouncing until it ends up going out the top, I guess, or until it leaves the stage, you might say. So there are better radiative transfer models out there, but they're very expensive, right? They're too expensive to run in the operational environment. Which does raise kind of another interesting issue here, which is that we are starting to look very seriously into emulators for these forward models. So to build an emulator, you just, you gotta give me some inputs to F1 and some outputs from F1, and then I can do my neural network thing or whatever it is I'm going to do, and I can learn that relationship, and maybe I can use that to speed it up. And in fact, we have some reason to believe that we can do that pretty well with the F1 that we're using here. But I guess the real question is, can we do it with a 3D radiative transfer model that's maybe more realistic? So that's not really an answer to your question, but that's the only answer I have.
Thank you so much.
Okay. All right, thank you. And that's it. I didn't even need the clock drawn. Okay, sorry for going over.